So the Turing machine model is largely considered to be sort of the most powerful, sort of actualizable model of computing that we could possibly have. And to make such a broad claim that we're not going to be able to actually develop any sort of computer that's going to be more powerful than a Turing machine is a very challenging claim to defend. So what we're going to do next is we're going to actually look at Alan Turing's original work, where he presents the Turing machine model of computing. We're going to talk about his motivation, how he settled on the various components of this model of computing, and then look at why we think that this is actually a pretty good representation of sort of anything that might be possible by finite means, anything that we could compute by any finite means at all. So that means any sort of computer or any sort of computing device that can be represented finitely, we think cannot be any more powerful than a Turing machine. So to start with, let's look at the inspiration for just this term of computer. So during Alan Turing's time, people had this idea that you could mechanically calculate various things, but when somebody said the word computer, it was still a relatively new thing that referred to some sort of automated mechanical device. It was more often the case that a computer was actually a person. So here we have a picture of the U.S. Bonus Bureau. So this is actually a team of people who are working to calculate Army bonuses. And each of these people you see sitting there had the job title of computer. So computers were somewhat morbidly named after the first job that they made obsolete, the first job that they replaced. And the important thing to look at here is that these computers, they're mostly women, first of all, and they're sitting at these devices that are sort of helping them to calculate the bonuses that various veterans were going to receive from the government. And these devices, it's sort of like a typewriter calculator type thing, and then they also have these spools of paper. So kind of the idea of a Turing machine, or this computing device, is that this spool of paper is sort of intended for some sort of scratch work, and then the finite state controller that's got those states and the transitions and so forth, that's kind of like the human that's operating that device that's going to manipulate the tape. So if we think about sort of how is it that we as humans try to go about doing calculations, we can sort of summarize how we might go about trying to solve problems or trying to compute functions in a way that sounds a little bit reminiscent of a Turing machine. So Turing was actually trying to formalize what humans do, basically considering that humans were going to be the most powerful computing device that a human could imagine. And so if he could create some sort of mathematical model that he could argue does everything that a human could do, then he's got a pretty strong argument to say that this is the most potent model of computation that might be relevant to us. So when we think about what you or I might do when we're trying to solve some sort of problem, perform some calculation, basically we're going to have some sort of state of mind. So this idea of a state in our finite state controller for the Turing machine is, Turing originally called that kind of a state of mind, where we sort of have in our minds what stage of the computation we might be in, what were the stages before, what are going to be the next stages, and so forth. So we had this sort of state of mind that we maintain while we were doing a calculation. And then we could also have some scratch work that we had. So maybe we had a piece of paper where we could take notes, so we could read notes that we had taken before, we could write notes. And essentially, the interaction of our state of mind and the contents of that paper are how it is that we go about doing pretty much any calculation at all. You want to do long division by hand, we have our state of mind for what it means to do long division, what stage we might be in long division, and we can read the long division problem off of the paper, and then make changes to that as we go to assist us in finding the answer to that long division problem. And those, if we squint real hard, those basic components are simplified but still present in a Turing machine. It has its states and its finite state automaton that's meant to be the state of mind of the Turing machine. And then we have that tape that is meant to be the scratch work, the notes that we're taking, that we're writing down and reading from in order to assist that computation. So what we're going to do is we're going to go ahead and look at actual snippets from Turing's original paper where he presents the Turing machine model of computation. He didn't call it Turing machine, by the way. That would have been presumptuous. But we're gonna take a look at this. Okay, so Turing says computing is normally done by writing certain symbols on paper. So we have these symbols that we write as we're doing long division, that sort of thing. So we may suppose that this paper is divided into squares like a child's arithmetic book. So this is kind of like saying maybe we've got lines on our paper, or grids on our paper, or something like that, just to help us keep things organized. In elementary arithmetic, the two-dimensional character of the paper is sometimes used, but such a use is always avoidable. I think it would be guaranteed that two-dimensional character paper is two-dimensional character of paper is no essential of computation. I assume that the computation carried out on one-dimensional paper, i.e. a tape, divided into squares. So basically what Turing is saying here is he's saying that you or I, we use this two-dimensional paper when we're taking notes, but he argues that anything that we could do on two-dimensional paper, we could also do on kind of a one-dimensional tape, a one-dimensional strip. So the fact that it's two dimensions is sort of irrelevant as we're trying to do computing. So he introduces this idea of this linear one-dimensional tape as our memory, arguing that that's not really going to be any different from the two-dimensional paper that humans use. So next he continues on to say, I'm also going to suppose that the number of symbols that may be printed is finite. So this is him saying that the alphabet, the symbols that we're going to be writing down on the paper and reading from the paper, that needs to be a finite set. So even though it might seem like there's continuous symbols that we might have, like maybe you've got a line that's a centimeter tall, and a line that's 1.1 centimeters tall, and a line that's 1.2 centimeters tall, and you could subdivide that and so forth. He argues that the set of symbols that we're going to be reading and writing from the paper must be a finite set. So he continues on by saying, if we were to allow for an infinity of symbols, then there would be symbols differing by an arbitrarily small extent. So if we had an infinite number of symbols, then we must have really, really similar looking symbols, is what he's saying here. The effect of this restriction is of the number of symbols is not very serious. It is always possible to use sequences of symbols in places of single symbols. So he essentially says that we should only have finitely many symbols. That way you don't have any symbols that are too similar, and if you really wanted more symbols, then that's no bother, because you can use sequences of symbols to represent additional symbols if you really needed more. So thus an Arabic numeral, such as 17 or a bunch of nines, is normally treated like a single symbol. So if you were going to be using Arabic numerals 0 through 9, but you really needed 20 of them, then you could just consider the combination 1-7 to be treated as a single syllable. A single symbol. So similarly, in a European language, words are treated as single symbols. So Chinese, however, attempts to have an enumerable infinity of symbols. Enumerable infinity means countably infinite. The differences from our point of view being that single and compound symbols is that the compound symbols, if they are too lengthy, cannot be observed at one glance. This in accordance with experience. We cannot tell at a glance whether this bunch of nines and that bunch of nines are the same. So he sort of makes this additional statement here to argue why the symbols should be finite, which is to say that we really want it to be the case that it's the machine itself that's doing the computation. If you have a bunch of symbols, then even distinguishing one symbol from another, or reading one symbol, is itself kind of a computation that needs to be done. So you would need some sort of procedure, some sort of algorithm to determine whether or not those two bunches of nines were actually going to be the same bunch of nines. So it seems like reading a symbol should be some sort of atomic operation that the machine is going to do. And if you have too many symbols, an infinite number of symbols, then it seems like that itself needs to be a computing procedure. So let's restrict ourselves to a finite number of symbols and just avoid that issue altogether. So sort of the next thing that he talks about is he talks about why the number of states has to be finite. So we mentioned that we have these states, which are kind of like the state of mind of the machine, and he argues that the number of states that are allotted in this state of mind has to be a finite number. So he says, the behavior of the computer at any moment is determined by the symbols which he is observing. Yes, he's using male pronouns here. And his state of mind at that moment. So these are the states in the finite state controller, each of which is a distinct state of mind, is what he's saying here. We may suppose that there is a bound B to the number of symbols or squares which the computer can observe at one moment. So there's some upper bound on how many symbols from the tape can be read. So in the model we've talked about, that bound is 1, but it could potentially be more. We might say that somebody can glance at several symbols at a time, but it's going to be a finite number. If he wishes to observe more, he must use successive observations. This is sort of this thing where looking at a chunk of nines, you need to have multiple observations or some procedure to figure out how many nines there were in that chunk. So that's sort of why there's this upper bound B. We'll also suppose that the number of states of mind which need to be taken into account is finite. The reasons for this are of the same character as those which restrict the number of symbols. If we admitted an infinity of states of mind, some of them will be arbitrarily close and will be confused. So if we have an infinite number of states of mind, then a lot of them are going to be really, really close to one another, and you're not really going to be able to say that those states of mind are distinct from one another. So the computer would get confused about which state it was in if there were infinite possibilities. So basically what Alan Turing has done here with this paper is he's compared the formal mathematical definitions of his model of computing with what a human does, and sort of explains why all of the things that the computer that his computing model do have parallels to how a human might operate, and that these restrictions that he put on his definition seem like they are reasonable restrictions because a human would have those same limitations as well. It seems unreasonable that a human would be able to, at a glance, distinguish arbitrarily similar symbols from one another, and it also seems reasonable that a human would not be able to have an infinite number of different states of mind, so to speak. So as long as you buy that there is no procedure a human can do to assist with computation, different from having a state of mind, reading from and writing to a paper, and you agree that the number of states of mind must be finite and the number of relevant symbols a human could use must be finite, then he's sort of arguing you have to believe that this Turing machine model does everything that a human can do.